Good morning, everyone. It's a pleasure to welcome Professor Gia-Wei Chern from University of Virginia, who will be talking about multiscale dynamical modeling of correlated electron systems. Gia-Wei started his academic career as an electrical engineer, getting a PhD in optoelectronics from Taiwan. And then he decided to switch to theoretical condensed matter physics and moved to Johns Hopkins University, where he got a second PhD degree in theoretical condensed matter physics. After which, he moved to University of Wisconsin as an ICAM postdoctoral fellow, and subsequently moved to Los Alamos National Laboratories, where he was an Oppenheimer Fellow, which is the highest honor awarded to postdocs in Los Alamos. And in 2015, he moved to University of Virginia, where he has been ever since. Gia-Wei's research interests are in quantum magnetism in general, and in particular, frustrated quantum magnetism. A big part of his research involves the interplay between electronic and spin degrees of freedom in the presence of strong correlations, which is an incredibly difficult yet incredibly rich field. Today, he will give us some insight into his recent work on multiscale dynamical modeling of correlated electron systems. Gia-Wei, all yours.
Okay, thank you. Thanks, Pinaki, for the nice introduction and for the opportunity to present our recent works. So as Pinaki said, I'm going to talk about multiscale dynamical modeling of correlated electron systems. And so mostly this involves the development of new computational materials for correlated electron systems, and also involving using machine learning methods to enable large-scale dynamical simulations. So most of my work is supported by U.S. Department of Energy. Okay, so first, compressed nanoscale textures are ubiquitous in correlated electron materials. Here I show some canonical examples. For example, this is an MFM image of the phase separation in this manganite material. So here the blue and the red regions represent the insulating CDW domain and the metallic domain, respectively. And the second one shows the this inhomogeneous state of this canonical Mott insulator VO2 during the Mott metal insulator transition. And the third panel shows this inhomogeneous pair superconducting pairing amplitudes in this bismuth 2212 cuprate superconductivity conductor. And the last one is this inhomogeneous state of another Mott insulator during resistive transition. So you can see that inhomogeneous states are ubiquitous and everywhere in strongly correlated electron materials, and they are not only of fundamental interest, they are also they also play a crucial role in the emergence of novel macroscopic functionalities. For example, in colossal magnetoresistance, this phase separated scenario is important for understanding why we only need a moderate magnetic field in order to achieve huge changes of resistance. That's mainly because even without the magnetic field, you already have many ferromagnetic domains embedded in this insulating matrix. And the magnetization of these ferromagnetic domains, these are metallic clusters, they point in random directions. And once you apply even a small magnetic field, you sort of align all these magnetizations into the same direction, then this can significantly reduce the resistance. And it is also, this inhomogeneity also plays an important role in the mechanism of high at least in one series for the high temperature superconductivity that involves the stripes and checkerboards patterns. And finally, in homogeneous states, also very important for understanding the resistive switching phenomenon in conventional materials and also for strongly correlated materials. So to model this in homogeneous states, intrinsically we need a multiscale methods, and that means it's a computationally very difficult task. On one hand, one need to do a proper job of microscopic electronics dynamics modeling that involves from a straightforward exact diagonalization to more sophisticated methods like dynamical mean field theory or quantum Monte Carlo. Pinaki is an expert in these methods, or density matrix renormalization group, and these are all very time consuming. But on the other hand, in order to model this inhomogeneous phenomenon, we also need to do large-scale macroscopic pattern formation simulations that involves kinetical Monte Carlo methods or molecular dynamics, or for spin systems, non-Lewis Gilbert dynamics. So on one hand, you need to do time-consuming microscopic calculation. On the other hand, you also need to do large-scale simulations involving many electrons. And so fortunately, recent machine learning methods, especially this deep learning neural network, provides a promising solution for these difficult numerical problems in bridging this time-consuming microscopic electron calculation and this macroscopic pattern formation simulations. So this idea is not new. People in quantum chemistry and the material science, they've been looking into this for almost 20 years. Here I show some of the important papers in this direction. For example, this paper by Baylor and Parinello has been cited by more than 1,800 times. So in their community, they want to do like this so-called ab initio molecular dynamics simulations. So this is a kind of molecular dynamics methods which computes the force by solving the Schrodinger equation exactly, or within this density functional methods framework. And since this practically this involves solving the constant equation, and this takes a lot of time, so they already figure out how you can use a neural network to emulate this time-consuming constant equation solution, and then directly predict the force which is needed for the molecular dynamic simulations. We'll come back to this in our talk. And in this work, our main goal is to apply this idea of deep learning neural network potential to well-known lattice models in condensed matter systems. So the first example is the phase separation in these manganites. And perhaps the simplest model which can exhibit this phase separation phenomenon is this single band double exchange model. And here is the Hamiltonian of this model. You have the first term here describe spin electrons with spin up and down hopping on a lattice. Here I showed an example of a linear chain. So the hopping amplitude is T. And then the second term is a local Wundt coupling, which try to align the spin of electrons to local spins. So in the double exchange model, you have a classical spin S on every side. So when electrons hop between on the lattice sides, its spin will be try to align with the local spin. And J is this Wundt coupling constant. So in this work from Dagoto's group, they use various different methods like DMRG, exact Monte Carlo, exact diagonalization Monte Carlo, and also DMFT methods. So they have obtained the phase diagram of this single band double exchange model. The x-axis is the average number of electrons per site, and the y-axis is the ratio of the spoons coupling to the electron hopping. So when n equal to 1, that means in average you have 1 electron per site, and that corresponds to half filling. And along this half filling line, you have a perfect nail order as the ground state. Once you drop a little bit of holes or removing some electrons, then you immediately have this region of electronic phase separation, PS here. And they saw this phase separation region in 1D, 2D, and DMFT calculation, which corresponds to infinite dimensions. So like I mentioned, this electronic phase separation is very important for understanding this colossal magnetoresistance phenomenon, as nicely discussed in this book by Dagoto. Okay, so now here we want to simulate this phase separation phenomenon, which means we want to perform dynamical simulations for the spins. And that means we need to solve numerically this stochastic Landau-Lewis Gilbert equations. So it describes this ds dt, and the first term is a precision dynamics, and the second term is a damping. Which try to align the spins to the local effective field direction, H. In the following, we will also call this H the force acting on spins. And this zeta is a thermal noise for the spins in proportional to temperatures. So to perform this kind of LLG simulation, the most important part is the calculation of this force or effective field H. And so in so-called classical LLG simulations, this force is computed from the minus the derivative of some effective energy with respect to spin. And the effective spin Hamiltonian can be written like this Heisenberg type term, or the Rashinsky-Moria and force spin interaction and so on. So you have this explicit effective spin Hamiltonian, and the calculation of this force is straightforward and can be done very quickly. So classical LLG simulations can be done for very large system, mainly because the force calculation is cheap and can be done very fast. But in our case, we want to do a quantum LLG simulation, which means the force, in order to compute the force acting on spins, we need to first obtain the expectation value of the Hamiltonian. In our case, is this double exchange Hamiltonian, and then do this derivative with respect to spins. And you can see that that means you need to compute these matrix elements of electron correlation function, or sometimes called the single electron density matrix. So this takes a lot of time. And that's why if you do exact diagonalization for the spin dynamics of double exchange model, usually you are restricted to rather small system size. By the way, here we are doing so-called adiabatic quantum LLG simulation. That means the time scale of spin dynamics is much slower than the relaxation time of electrons. So then when we try to compute the force acting on spins, we can assume the electrons are sort of in quasi-equilibrium. And that's why here we solve the electron thermal states and then compute the Hamiltonian using these instantaneous electron states. So this is similar to the Born-Oppenheimer approximation in quantum molecular dynamics. But this exact diagonalization is too time consuming. So of course, we try to speed up this part. And there are all kinds of numerical methods, notably these kernel polynomial methods, which can be used to, which is a linear scaling methods. But here we want to show that machine learning methods can be also used to achieve efficient simulation for this double exchange model. So for this, we call the machine learning LLG simulation. And again, in this case, the force is again given by the minus the derivative of some total energy. We call this the machine learning energy with respect to spin. And then we develop a neural network potential for this total energy. First, based on locality, principle of locality, we partition this total energy into contributions from local spins. And this, so far, it is not explicitly defined what is this local energy, but it will come out automatically through training of the neural network. And then next, we assume that this local energy, which is associated with each individual spin, depends on only the neighborhood of this spin. We call this Ci through some universal functions. We call this epsilon Ci. Okay, and then to implement this universal function, we use the neural network, which means we fit the neighborhood configuration around this spin Si into a neural network. And then the output of this neural network is this local energy, right? So that means that this universal function is sort of encoded within this neural network. And most importantly, we train the neural network using exact solutions. Then once we successfully train the neural network, then the calculation of this local energy can be done very fast. So then we can use this to do large scale simulation at the same time with the accuracy of quantum calculations, mainly because the neural network is trained from the exact solutions. Okay, so more specifically, here I show how this deep learning spin potential works. So again, the total energy of the system in this machine learning model is given by contributions from local contributions epsilon I here. So let's consider in our lattice this particular spin Si, and we want to compute the force acting on this spin. So according to this principle of locality, we assume that the local energy epsilon I depends on only the neighborhood Ci. So neighborhood magnetic configuration means all the spins within some cutoff from the center spin Si. So this we call the local magnetic environment. But since the double exchange model has this global spin rotation symmetry, and we want our neural network model also to possess this spin rotation symmetry. So in order to achieve this, instead of just throw the spin configuration into the neural network, we assume that the dependence is only through the bound variables and the scalar chirality. So bound variable is all the pairs within this cutoff, like sj.sk, and the scalar chirality are all the spin triplets in this form within the cutoff. So by assuming that this universal function only depends on the bond and the scalar chirality, then automatically the spin rotation symmetry is respected. And finally, we also want to preserve the lattice discrete point group symmetry. And that means that we try to use all these bond and scalar chirality variables. We view them as a high dimensional reducible representation of the lattice point group. And then we decompose it to find all the irreducible representations. And then the local environments built from this bond and scalar chirality now are translated into these amplitudes of all the irreducible representations. And then invariants of the symmetry group called the feature variables are obtained from this so-called bispectrum coefficients of the amplitudes of all the irreducible representations. So in the end, we obtain some sort of generalized coordinates, x1, x2, x3, to a couple hundreds of them, and they represent this local environment configuration. But importantly, these feature variables, they are invariants under spin rotation and lattice symmetry operations. Now, once we have these feature variables, we fit them into a fully connected neural network. And then the output of the neural network is this local energy, epsilon I. Then we apply exactly the same descriptor and the neural network to every other spin in the lattice. Then we obtain epsilon 1, epsilon 2, epsilon 3, and so on. and we sum all of them to obtain the total energy. Then we do this so-called automatic differentiation. This can be done easily in PyTorch to get all the forces H1, H2 like this. So that's how we use the neural network potential to obtain the force. Once you obtain the force, then you can just use whatever algorithm to integrate the non-Dirichlet equation and get the new spin configuration. Okay, so for our double exchange model, we built a 6-layer fully connected neural network with 4 hidden layers. These are the number of neurons in each layer, and 554 is the number of the input layer, and this number depends on the number of feature variables from the descriptor. And there's only one node neuron at the output, which is the local energy. And training data sets are consist of 3,500 snapshots of exact solutions on a 30 by 30 lattice. And out of these snapshots, we choose 1,000 random configurations and 1,000 intermediate states from the random configuration and in between the random configuration and the fully relaxed phase separated states. And we also use 1,500 phase separated states. So for the training data sets, and although 3,000 doesn't seem to be a big number, but remember that for each snapshot, we have 900 spins, which means we have 900 force data. So 3,500 times 900 is a lot of forces to be used to train a neural network. Yes, and the loss function in our case consists of the mean square error of all the forces and the total energy. Okay. Right. So this figure shows the comparison of the predicted force and the exact force. You can see that they lie on this diagonal lines, which means the prediction is pretty good. But unavoidably you will have errors because of this cutoff and the machine learning training. But here we find that the error seems to follow a normal distribution. And later we can treat this machine learning prediction error as some sort of thermal noise. And we also test our neural network model on small 30 by 30 system. So here we compare the non-Dirichlet simulation using the machine learning potential and the non-Dirichlet simulation using exact diagonalization to solve the electron Hamiltonian. And here, these two figures shows the spin-spin correlation function at 2 different electron feeding fractions. You can see that the agreement between the machine learning model and the exact simulation is pretty good. So now with this benchmark, then we apply this machine learning model to simulate phase separation phenomenon of this double exchange model on really big systems. Here I showed a few snapshots of this simulation on a 200 by 200 system. So it's impossible to do exact diagonalization for this kind of system. It's okay to do exact diagonalization for one snapshot, which might already take a few minutes. But here you want to do a dynamical simulation, which means you need to do this exact diagonalization at every time step. And there are tens of thousands or hundreds of thousands of time steps. So, with the aid of machine learning, we are able to achieve this large scale and long time simulations. We also do this did this for smaller systems, 100 by 100, in order to see some fine features. You can see that the top panels shows the spin correlation, nearest neighbor spin correlation. So the red area means ferromagnetic spins, and the blue area means antiferromagnetic spins. So you can see that you have a lot of antiferromagnetic regions, but a few of these ferromagnetic islands. And in the bottom panels, here I show the local electron feeding fraction. So 0.5 corresponds to half feeding or 1 electron per site. So you can see that this antiferromagnetic regions corresponds to half filling and corresponds to the Néel order. And these ferromagnetic regions corresponds to low electron concentration, or you can feel like the doped holes aggregates to form these ferromagnetic clusters. So that's what we call the phase separation. After you dope these holes, they try to stick together to form these clusters, and within these clusters, spins are sort of parallel to each other. Okay. So next, we want to understand what is the domain growth of these ferromagnetic clusters of these hole rich regions. So to understand the theoretical background, we know that since the number of doped holes is a conserved number, so the phase separation dynamics of this kind of conserved order parameter was originally considered by Lifshitz, Stylozov, and Wagner. So they, in this theory, since the you have a majority face this white area and the minority face these gray areas. And in order for this minority phase to grow, since the number of minority phase particle is conserved, so in order for this one to grow, you need a smaller one to first evaporate, and then for these minority particles to diffuse and migrate to the larger clusters. Then this minority phase can grow. And by working out details of this, they found that the characteristic size of this minority phase will increase with time follow this power law with an exponent of 1/3 for all dimensions greater than 2 or equal to 2. And numerically, this process can also be described by this Kahn-Hilliard-Cook or model B equation. And so you can use so-called cell dynamics methods or Monte Carlo or phase field simulation to simulate this domain growth process. And this 1/3 law has been numerically confirmed. And people also find the dynamical scaling. So then the question is whether this 1/3 domain growth law also apply to our case, which is describe the domain growth of these hole-rich ferromagnetic clusters. So again, this shows the nearest neighbor spin correlation, and this figure shows the histogram of the nearest neighbor spin correlation. Initially, in the random states, we have a flat distribution, and at the in the late times of the phase separation, you see there's a peak at B equal to -1, which corresponds to this anti-ferromagnetic correlation, and B equal to 1, which is the ferromagnetic correlation. So the appearance of these two peaks means the phase separation phenomenon. So the system separate spontaneously separate into some ferromagnetic clusters embedded in anti-ferromagnetic background. So now with this, we can try to compute the size of these ferromagnetic clusters represented by this peak. So initially, the size of the ferromagnetic cluster decreases. That's because even in a random state, you have sort of large enough ferromagnetic clusters. But now during the phase separation, the anti-ferromagnetic background is being established. So then this size ferromagnetic cluster size decreases, then start to increase again. So the question is whether this increase of the ferromagnetic clusters is can be described by this LSW power law. And it turns out it cannot. You can see that this LSW power law can at best only describe the initial part of the domain growth. And at that times, the growth of these ferromagnetic domains is significantly slower. In fact, it is better described by a sublogarithmic domain growth. So the question is why the breakdown of this LSW growth law? And the reason is because of the formation of these so-called magnetic Polarones. These are, small magnetic ferromagnetic clusters which confine a few and sometimes just exactly one doped holes. And once the antiferromagnetic order in the background is fully established, then these doped holes, they are completely confined in these ferromagnetic clusters, and they lose the mobility to move around. And because of this sort of self-confinement of doped holes in the ferromagnetic clusters, then this LSW mechanism does not work, because these carriers, they cannot move around. They cannot evaporate from the small clusters and then migrate to larger clusters. And that's why the domain growth sort of stopped. Right. And interesting question is whether quantum fluctuations. So here we treat the spins as classical spins, but if we include the quantum fluctuations of these spins, whether this might restore the LSW law is unclear. Okay, so in the second case, we apply the machine learning methods to study the phase separation phenomenon in another canonical correlated electron model, which is this follicle Kimbo model. Again, and we consider the spinless case. So you can view this model as consisting of two types of electrons. One is the C electron, the other is the F electron. These F electrons, they are heavier and sort of localized. So we can treat them as classical degree of freedom. So this F electron occupation number NF is either 0 or 1, sort of like an Ising spin. And then, when the C electron and F electrons, they happen to be on the same side, there's a repulsion U. So this term is sort of to describe this correlation effect in this model. Okay, and so earlier work has shown that this model has a very rich phase diagram and all kinds of complicated structures. Like this is a checkerboard CW pattern. And you also have vertical stripes or diagonal stripes, or even more complicated structures with large unit cells. So in this work, we want to study the phase separation of these checkerboard CW patterns. So conventionally, people, since the C electron here is quadratic, so you can again use exact diagonalization to simulate this system. So people combine Monte Carlo methods with exact diagonalization to study the equilibrium phase of this follicle Kimbo model, or you can do real space DMFT. In this case, it's not as exact as the Monte Carlo plus ED. It's within this DMFT approximation, but within this approximation, the problem can be solved exactly. And with real space DMFT, people also find all kinds of inhomogeneous phase. And here we want to do non-equilibrium dynamical simulations. Again, we assume adiabatic approximation, which means that the random walk of this F electron, the time scale of the F electron dynamics is much slower than the relaxation time of the C electrons. So for dynamical simulation, we want to do this random walk simulation of the F electrons, like a trajectory shown here. But in order to move this F electron around, since the F electron interact with the C electrons, so we use this metropolis or global dynamics. But to compute the transition probability, you need to find the energy difference before and after you move it. And this involves diagonalizing the C electron Hamiltonian. Right? And in order to decide which direction to move this F electron, you have to consider the possibility of moving upward or downward to the left or to the right. So then you have to consider 4 possible after states. And that means in many cases, you need to do 4 exact diagonalizations for each update. And that takes a lot of time for just moving one F electron. So this is a super time consuming process, even with exact diagonalization only. Right. So in order to speed up this process, again, we develop a deep learning neural net model. So the goal is to use the machine learning to directly predict this transition probability, right? And we also assume this delta E, the energy difference after and before the update, only depends on the neighborhood configuration of the F electrons, and then we do similar descriptor to find the general coordinates which are invariant under symmetry operations. And then we develop a neural network to directly predict these 4 different energies when you move the F electrons up, left, down, or right. And in this case, we include some convolutional neural network at the beginning. I mean, after the descriptor and before the fully connected neural network. That's mainly because here the F electron occupation is 0 and 1, so it's a discrete variables. And CNN usually is very good at extracting some major features from this kind of discretized input. Okay, so this slide shows the benchmark of our neural network model on smaller systems. This is the prediction of the energy. And here is the simulation, kinetic Monte Carlo simulation on smaller systems. And you can see that the agreement, although there are errors with the prediction, but the overall agreement is pretty good. Then we applied the benchmark neural network model to perform large-scale simulations. So basically, we want to do a thermal quench simulation. So initially, these dots are the positions of the F electrons. So initially, the F electrons are in completely random configuration, and then we suddenly quench the temperature to a very low temperature. And then these F electrons, they are doing this random work and try to segregate and form these CDW checkerboard patterns. So you can see that yes, some small checkerboard patterns can be seen at late times of the phase separation. And this figure shows the average size of the checkerboard as a function of time. And you can see that the size is actually pretty small. Even at very late times, the size is like less than 12. Like, you know, here shows a zoom-in picture of this next stage configuration. And you can see that here is one CDW cluster, here is another one, here is another one. And somehow they sort of also stop and they don't try to form an even larger CDW. And the number of, since the number of F electrons is also conserved, so again, we expect this phase separation or domain growth to follow this LSW 1/3 power law. It turns out it sort of followed the power law only for a very small period, and then later it deviates from the power law. So the domain growth also significantly slower. All right. So this seems to be the end of the story, but we noticed something unusual during this phase separation process. So to see this, we try to we use different colors for F electrons when they reside on the A sublattice or the B sublattice. If the F electron is on the A sublattice, then we color them red. If they are on the B sublattice, we color them with blue color. And after this coloring, you can see that although this F electron CW cluster is still very small, but the red clusters, they try to stick together, and blue cluster, they try to stick together. So there is some sort of supercluster formation during this relaxation process. Right. So that means even though the CW cluster growth is very slow and the CW cluster itself are small, but there's a hidden AB sublattice symmetry breaking corresponds to this formation of superclusters. By superclusters, I mean these superclusters of cluster of the CDW checkerboard patterns. And this supercluster formation can be described by an effective Ising order parameters. So we introduce an Ising field to represent this red supercluster or this blue supercluster. You can see that with the corresponding Ising order parameter sort of grows with time. So there's a hidden coarsening of these Ising domains. Next, we try to study the domain growth of this supercluster instead of the CDW cluster. We already know CDW cluster initially follow this LSW law, but then are sort of frozen. Now we want to look at the domain growth of the superclusters. And again, it initially also follow a power law. You can see this from the log-log plot of the characteristic size of superclusters. And also at daytimes, it deviates from the power law, means the domain growth is slower. And this figure shows a dynamical scaling. So after proper scaling the structure vector at different times, they collapse on a sort of universal curve. That means dynamical scaling. And so the conclusion is that there's a novel coarsening of superclusters. So in this phase separation, we have domain growth on smaller CDW clusters and also on larger superclusters, which are these aggregates of CDW clusters. But both cluster growth in the end are sort of slowed down and kind of arrested. And the reason is because once you have a supercluster, once you have a CDW cluster represented by this black region here, it sort of creates this staggered potential in the neighborhood. So this color bar shows the effective potential for the F electrons, and we obtain this from Monte Carlo simulation. We put a test particle in the neighborhood of this cluster, and we just do a bunch of Monte Carlo simulation, and to see how many times the test particles stay at one particular site. And then from this frequency, we can obtain an effective potential. You can see that there's a staggered potential in the neighborhoods. And as the CW cluster or the supercluster size grows, this contrast between A and the B sublattice also increases, which means once you have a very large supercluster, the difference or the energy barrier between the A and the B sublattice becomes so large such that although the F electron want to join this cluster, but it cannot overcome the barrier to jump even to the neighboring B sites. And that's why both the CW domain growth and the supercluster domain growth both frozen at their times. Okay, so I think I have like 10 minutes or 15 minutes left. So I'll quickly go over our efforts on this molecular dynamics simulation for correlated electron systems. So molecular dynamics is very important in material science and all kinds of physical science. And people use molecular dynamics to study equilibrium or non-equilibrium phase transformation, nucleation phenomenon, and like elastic properties of nanotubes, membrane, proteins. But so far, and you can see this, the number of molecular dynamics papers steadily increase with time. So it's a very important tool in material science. But even the state-of-the-art molecular dynamics methods do not properly include the strong electron correlation effect. So our goal is to develop a new molecular dynamics methods which can properly incorporate the electron correlation effects. And for example, then you can use it to simulate this metal insulator transition, Mott transition, which is a typical phenomenon of correlated electrons. So what is molecular dynamics? Essentially, it's just solving Newton's equation of motion. And in most molecular dynamics simulations, we just use the second order velocity Fourier algorithm to integrate the atomic positions. But similar to this non-Lorentz simulation, the most difficult part, most important part is the calculation of the force. And for classical, so-called classical MD simulations, the force is computed from the derivative of some empirical energies, E. And in these empirical energies, you have, for example, this term which will constrain the bond length, and this term which will constrain the bond angle or the dihedral bond angle. And you can also include this Lennard-Jones dependence or electrostatic interaction. So similar to this explicit spin Hamiltonian, here you have an explicit energy potential. So the calculation of this derivative is straightforward and can be done very efficiently. So that's why classical MD simulations can be done in very large systems. And this shows the sort of the state of the art of what classical MD can be done. So people now can do like up to 10 to 8 number of atoms, and also run for a pretty long simulation times. So this is an example of a recent large-scale simulation. So people use this empirical force field called Chern to simulate this crystallization of this protein envelope for this H1N1 coronavirus. Right. So challenges in classical MD is just how large the system you can simulate and how long time you can simulate, and that means if you have more money, you can use more parallel computers, and then you can do larger size, longer time simulations. But the accuracy is not improved, especially for situations involving chemical reactions, or if there's a charge transfer, a bond breaking, and also in particular, the electron corrosion effect, like metal insulator transitions. So these phenomena are sort of beyond the classical MD simulations. Right. So there's in order to improve the accuracy to describe some of this charge transfer or bond breaking phenomenon, people also can do quantum MD. And so this means we keep the electrons in the MD simulations. This is similar to the quantum LLG simulation. So again, we use just velocity rate to integrate the atoms. And for force calculation, now you need to solve the many electron wave function, and then you compute this expectation value of the Hamiltonian, and then you do the derivative to get the force. Okay, but in most cases, there's interactions between the electrons. So this is a difficult many-body quantum problem. So some approximations has to be introduced. And once you use whatever many-body technique to solve your many electron Hamiltonian and get the wave function, then you can use Hellman-Feldman theorem to compute the force. And once you have the force, then you integrate to get a new snapshot. Okay, so the state-of-the-art quantum MD is based on density functional theorem or the implementation through the Chern scheme. So in this quantum so-called DFT MD, so once you have a snapshot, then you solve this self-consistent Chern equation. And that means you have to iterate between solving an effective Schrodinger equation. And from the eigenstate, you compute the electron density. And this density will enter this exchange correlation functional. And then you have to iterate between these two to get the self-consistency. Then once you get the wave function, you can compute the force. Right. So although this DFT MD has been very successful in describing a wide range of materials, but it is known that the DFT methods cannot describe strong electron correlation effect, especially Mott metal insulator transitions. So we want to go beyond these DFT methods and develop a new quantum MD based on the Gutzwiller methods. So why Gutzwiller methods? So this is perhaps the simplest methods which can successfully describe the correlation-induced Mott metal insulator transition. And it is equivalent to a spatial slave-boson theorem. And it can be viewed as the Hartree fork of the mean field theory of Mott metal insulator transition. So although there are more accurate methods like variational quantum Monte Carlo or dynamical mean field theory, but these are too time consuming to be combined with MD simulations at this stage. So the basic idea of the Gutzwiller methods is you start from some Slater determinant states, like the one you obtain from time binding model or DFT calculation, and then you try to apply this Gutzwiller correlator or projector to this Slater determinant state. And the idea is in this projector, you try to reduce the statistical weight of the double occupied site, because 2 electrons in this site encode more energy. And Gutzwiller also introduced an approximation which can make the calculation of this off-diagonal matrix elements much faster. Right. So, so this is the flow chart of the Gutzwiller MD. So again, you have velocity for atoms, and then at every time step, you need to iterate between solving a renormalized time-binding electron Hamiltonian and solving an effective Hamiltonian for the slave-bosons, and then iterate between the two until you reach consistency. And then from the solution, this Gutzwiller wave function, you can compute the force. So here we apply this Gutzwiller molecular dynamics methods to simulate a toy model, which we call the Hubbard liquid model. So in this model, you have a time-binding electron Hamiltonian, but the time-binding coefficients now depends on the atom configurations. So this Tij sort of decays exponentially with the separation of the two atoms. And then we add a Hubbard U to describe this short-range repulsion when 2 electrons happen to hop to the same atom. And then we include a phenomenological pair potential. This is mainly repulsive. So because the electron will provide the attractive force, and you need a repulsive force to maintain stability of the system. And you can feel this pair potential of the short-range co-core repulsion. And finally, you have the kinetic term for classical kinetic energy for the atoms. And then we do this Gutzwiller molecular dynamics simulation for this atomic liquid, and we find a Mott transition. And this figure shows the histogram of the double occupancy. Right. So with these methods, we can, for the first, here I just want to mention that this toy model we call the Hubbard liquid model seems to be a very artificial model, but it turns out it can be used to describe the alkali fluids in this column. So experimentally, people already seen the metal insulator transition in like rubidium or cesium liquid metals. So our results can be used as the minimum model to describe the metal insulator transition in for these materials. Okay, so with these methods, for the first time, we can also look at how the electron correlation affects the atomic configuration for liquid states. And this figure shows the pair distribution function of these atoms in this Hubbard liquid. So G of R gives us the probability of given an atom at the origin, what is the probability of finding another atom at the distance R from the origin. And so for a small Hubbard U, you can see that the G of R looks like this. There's a peak at some equilibrium position. This corresponds to a dimer peak, which means these atoms, they like to form a molecular, like a H2 molecular. And when you increase Hubbard U, this molecular peak is suppressed. And when U is larger than the critical value, you get a totally different pair correlation function. And then for the first time, we can also compute both the electron conductivity and the atomic diffusion constant and how they depend on the electron correlation. So for electron conductivity, you see there's a non-monotonic behavior. The conductivity actually increases when you approach the Mott transition and then drop to 0 in the Mott insulating phase. But the atomic diffusion constant also has a similar non-monotonic behavior, which has a peak close to the critical point. And we confirm this with some classical chamber and isotope theory calculation. Okay, and recently we also further generalized our molecular dynamic methods. Instead of using the Gutzwiller, we use the DMFT solver. So the DMFT methods is based on the green function methods. And essentially, first you have this Dyson equation for the electron Green's function, and all the interaction effects is sort of incorporated into this safe energy. So there are all kinds of Feynman diagrams here, and the DMFT approximation essentially assumes that this local safe energy is local. It only there's no offsite correlation. Then within this approximation, the Dyson equation can be exactly solved, and so so different kind of numerical methods can be used to solve this safe energy. And so we recently also developed a quantum MD scheme based on this dynamical mean field theory. So it's highly parallel, but still, even with a lot of parallelization, so far we can only do like 40 atoms and 40 cores. And this is the result of our DMFT MD simulation. So the one important point I want to make is this is the first MD simulation which can show the spectral function of the electrons. Even DFT MD, because it is based on an effective single particle Schrödinger equation, so it doesn't give us this electron spectral function. In particular, with DMFT MD, we can see that there's this quasi-particle peak appearing when you approach the critical point, and then in the Mott phase, the quasi-particle peak disappeared, and then you have these two Hubbard bands. And these Hubbard bands are incoherent electron excitations, which is beyond both Gutzwiller and the DFT calculations. Okay, so finally, we also developed a machine learning potential for our Gutzwiller molecular simulations. So like I mentioned, we want to simulate this Hubbard liquid model with the Gutzwiller methods. But this Gutzwiller calculation, it involves diagonalizing a renormalized electron Hamiltonian, and then you have to solve this slave-boson Hamiltonian, and you need to iterate between these two. So it takes a lot of time, more complicated than just exact diagonalization for the double exchange model. So that means machine learning methods can really help with the efficiency of this kind of quantum molecular dynamics simulations. So the central idea is very similar to the one we discussed for the double exchange model. So again, for example, if we want to compute the force of this atom, we assume the local energy only depends on the neighborhood around this atom. So we take the neighborhood configuration and fit it into a descriptor. This will give us a set of generalized coordinates which are invariant under the symmetry operations of the system, like the rotation symmetry or the permutation symmetry. And then once you get these generalized coordinates, you fit it into a neural network and you get local energy. And then you do this for all the other atoms in the system. Then you get all the energies and you get the total energy. And then you do the same automatic differentiation to compute the force. So with this, we applied the neural network methods to our Gutzwiller MD simulation. And this is the force prediction. And you can see that with some errors, but the overall is pretty good. And here is the benchmark. We compare the MD simulation using the direct Gutzwiller methods and the potential from the machine learning model. And the agreement is also very good. And quite small. Surprising is even the pair correlation function obtained from the two methods are almost indistinguishable. So, so the neural network in this case was trained from data sets of exact Gutzwiller calculation and only 33 atoms. So it's a very small system. And once we have the trained neural network, we can do MD simulations on almost 3,000 atoms. And the results is agreeable, and also the speed up is almost 1 million times faster. Okay, so here is a summary and outlook. So here we show that new physics can be obtained by applying the machine learning methods to enable large-scale simulations. And for double exchange model and Faraday Kimbo model, with this machine learning enabled simulation, we are able to find an anonymous phase separation or phase ordering dynamics, which are beyond the classical series of phase ordering phenomena. And we also find, in both cases, we also find some freezing phenomenon, which we think might be a generic feature of strongly correlated electron systems. And we also develop a machine learning potential for a Hubbard-type model, like in this Hubbard liquid model with Gutzwiller methods. And in the future, we also want to develop machine learning potential for non-equilibrium electron forces. Thank you for your attention.
Thank you, Gia-Wei, for the nice talk. Any questions from the audience? Well, let me get started. Gia-Wei, if we go back to the very beginning of your talk, where you discussed the nature of this machine learning simulation.
Yes.
First of all, in the general approach, what is the difference from classical Monte Carlo simulation followed by exact diagonalization of the electron Hamiltonian and then resetting the this one?
Yes. Oh, so right. Yes. So no, it's for this you need to diagonalize this Hamiltonian of the whole system, right?
Right. Right.
So it takes a lot of time. Right.
Right.
Right. So machine learning methods is essentially it try to give us empirical potential, but not written. Or you can view it as some sort of like this expansion, but for very complicated spin interaction with 2 spin term, 4 spin term, 6 spin term, 8 spin term, and so on, and with all kinds of coefficients. So if you can manage to obtain all these coefficients from some fitting, then it's pretty much the same as machine learning. But here, since this is too complicated, so we just use this machine learning training methods to automatically obtain this neural network. And all the parameters are sort of encoded in this neural network.
I see. So yeah, that was precisely what I was asking, that if I look at this this blow up of the SI spin, then if as you say, somehow I can get all the parameters, then I'm effectively doing a classical simulation.
Yes,
okay.
Exactly. So
the next question is, can we adopt these symmetries that you mentioned, these bond, scalar chirality, irreducible representation of lattice point groups, into classical simulations of lattice spins? I'm thinking about 3D complex structures like these hedgehogs or Hopfians, etc.
Oh, no, yes. So this symmetry, this so-called descriptor part is very important. People in quantum chemistry, they already realized the importance of a good descriptor. It is even more important in their case. And so in quantum chemistry, people develop all kinds of descriptor, ACSF, Coulomb matrix, or bispectrum, and so on. But here, for lattice models, if the structure is simpler, the descriptor might not play a crucial role. But for spin system, for example, if you want to ensure the global rotation symmetry of your machine learning model, you need to do this descriptor, right? And so this symmetry we're talking about is just the lattice and rotation symmetry of your Hamiltonian. And so that means, for example, you take this spin configuration and then you fit it into your neural network, you get a certain energy, right? Now you rotate every spin by some angle globally, you expect to get exactly the same energy.
Certainly.
And so you need to do this descriptor in order to ensure this property. And once this is done, then you can use this to simulate like skirmions or whatever, right?
Okay.
Right. So I mean, although the magnetic states breaks the symmetry, but the the Hamiltonian possess this symmetry.
Absolutely, absolutely, yeah. Okay. Any other question from the audience? Okay, if not, let me ask another question. In the last part of your talk, where you talk about this growth of electron conductivity with respect to with varying Hubbard potential.
Yes.
Yeah, this one. So
yes.
If I now try to understand the behavior of real alkali metals in terms of this, does it mean that hydrogen has the highest value of U, effective U, and then you jump to sodium and then slowly decrease towards cesium? But that's too naive.
No, yes, right. So, hydrogen indeed, if you compute if you have some orbitals, electron orbital, and compute the Hubbard U, hydrogen indeed has the largest U compared with rubidium or cesium.
Okay, so that is consistent with this.
Right, but its Harpin constant is also largest.
Oh, okay.
Right, and what is important is the ratio of U and the bandwidth. That's because hydrogen are smaller, so their Harpin amplitude is also larger. But for rubidium or cesium, it's huge atoms. So the valence electrons is right. So then they also have smaller Harpin. So in the end, the sodium and the rubidium are still more strongly correlated than hydrogens.
But they are metal, whereas hydrogen is an insulator, right?
Hydrogen is actually a little bit different from the other alkali. I don't know those in the middle are close to hydrogen or the cesium, but like for cesium and rubidium, they in the metallic phase, they actually form more like a cluster of atoms. But hydrogen, and then this cluster of atoms is a metallic state, and then undergo this small transition. When for example, you increase the temperature and you expand the volume. Hydrogen is very different. In the liquid phase, hydrogen, they like to form molecules like here.
Yeah.
Right, and molecular is actually an insulating state. Although electron hop around, but it's only hopping between the two atoms.
Between the two atoms.
Right. So that's why the conductivity is small here, because it's essentially a molecular liquid, which is an insulator.
Nice.
And when you increase U, these atoms, they start to sort of dissociate a little bit, and then a larger network can be formed. That's why this conductivity sort of increase. So for hydrogen, there might be a small window of metallicity. Right. Okay, and before the molecular and the right.
I had one more question about this. You showed in this hidden sublattice symmetry breaking.
Yes.
Is it there that you have this effective, or maybe not, maybe even before that, where you have this single sites being with a single hole as ferromagnetic clusters.
Oh, you mean the double exchange model?
Yeah, the trapped. Yeah, exactly. So now, if I look at these description, is it in the same does it map to this Nagaoka state of, in the Hubbard model, if you go away from, if you dope away from the half filling by one hole, then you get a full ferromagnetic state. That is a theorem by, I think it's Nagaoka, but I may be mistaken about the name.
Right, Nagaoka ferromagnetism, yes, but I mean the situation, the setup might be a little bit different, because we know Hubbard model if you move a little bit away from half filling, it actually also phase separate.
Right, right.
It actually is very similar to the double exchange case, although the mechanism is slightly different, but it's similar. But I think Nagaoka ferromagnetism is in Hubbard model, but some sort of different settings. I also don't recall the exact.
Okay, because I saw this, that you have this blocks where you have one hole, and that's exactly those are the ferromagnetic blocks.
Right. But the one hole here are sort of trapped by these 5 spin clusters. So here it's more like a Polaron.
Okay.
Right.
Okay. Are there any questions from the audience? If not, since it's getting late, I think we should thank the speaker once again. And for a wonderful talk, and it's telling us about something very new and
my pleasure.
very fast developing. Okay, so thank you, Gia-Wei.